So here is the driver's side, the Australian driver's side, or what we call the right-hand side of the Cleveland block. And here at the rear, this machine pad has been cut down. If you notice the one on the front, it protrudes out, and it's also got an accessory boss right here, and that's usually where the earth strap is connected on the Ford Australia cars. And so to clear the exhaust manifold that Ford manufactured here in Australia, which tucked in really close and the exhaust exited around about this area here, they needed to remove the boss, the machining tab that was here, and to clear that exhaust manifold. Let me just show you on the other side of the block what I'm talking about. You can see here at the rear there is a pad that Ford used to hold the block while it was machined, and there's one on each of the four corners of the block. This is the case on just about every Ford V8 block, and it's not used for any other purpose other than holding the block during the machining processes, and so that's what we have. Now, going back to the beginning when I suggested that there were two things that I wanted to bring up with you, and that is the piston to deck height that Ford had on the Phase 3. Now, generally, the standard engines that came out from the factory, the 4 barrels, had approximately in between maybe 25 and 30 thousandths of an inch of deck clearance between the top of the piston here and the top of the deck, or the deck of the block. And so that allowed for lots of variations in conrod length, piston pin height, machining tolerances of the block, of the deck height. You know, there could be an accumulation of clearances that when it's stacked up, the piston could either be somewhere, you know, between, you know, 20 and 30 thou, maybe even from the deck. So what Ford Australia did is when they got their standard 4V short motor, they pulled it apart and they proceeded to machine the deck because they wanted more compression. The fuel at the time was what they called super, which had, you know, possibly in excess of 100 octane, and it was leaded, and so it was not really prone to detonation as easily as our fuels are today. So in their infinite wisdom, Ford Australia pulled the short motors apart and proceeded to surface the deck of the block approximately 25 to 30 thou, which gave them pretty much a zero deck height. You know, they probably didn't want to come above the deck, and so, you know, I'm not sure exactly, but that's the approximate measurement. Ford just decided to take a 32nd off, a 32nd of an inch, which is approximately 32 thou, or about 30 thou. And that will bring the piston up to the top. And once you bring the piston up to the top, that means that there's more compression, there's a smaller area for the combustion process to take place. And so the Phase 3 engine went from a standard 4V compression, which was probably around about 10 to 1, up to closer to 10.75 to 1, or what they thought was close enough to 11 to 1 compression. And so instead of using a lumpy top piston like in a Boss 351 in America, they just did their own thing, machined the block, used the cast pistons that came out of that original engine, put them back in, and so they had a flat top. And I don't know if they knew back then, but having a smaller quench area here in the piston, a narrower quench area between the flat spot of the cylinder head, and let me just show you the flat spot in the cylinder head that I'm talking about. See these flat spots here there's a flat spot here and a flat spot here and another flat spot here. So we have three areas of the cylinder head that the fuel and air mixture is squashed so much that it needs to escape into the combustion area. And so that's why these are called quench heads, because it quenches the fuel and air mixture into a tighter area. And so engineers, race engine engineers have figured out over the years that the smaller the area between the top of the piston and the quench area here, the better for making horsepower. And so there is a minimum that you can have for that gap, because if it's too small, let's just say too small is 5 to 10 thousandths of an inch, the fuel and air that is in that area may not be able to escape and will combust under pressure and not under the flame front of the combustion process. And so you'll get preignition or detonation caused by the fuel and air mixture being ignited by compression. It'll be like a diesel engine. And so the boffins in the racing world have figured out that approximately somewhere between 40 thousandths of an inch and 35 thousandths of an inch is the optimum distance to have between the flat area of the cylinder head and the flat area of the piston. And that is enough space to allow the fuel and air mixture to get squashed out and into the combustion area, and it's not quite small enough for the air and fuel mixture to just ignite on its own just through a pressure squish. So I'm probably not using the exact terminology that the automotive engineering realm uses, but anyway, hopefully you get my idea. So Ford back then, whether or not they realized it, they were producing a sort of like a development in the area of combustion process that was ahead of its time. And so I'm guessing that all they wanted to do was increase compression. They didn't realize that what they were doing was improving the combustion process as well by creating a perfect, almost perfect squish area. Now they would have been using head gaskets that were approximately 1 millimeter to 60 thousandths of an inch, like 40 thou to 60 thousandths of an inch thick. And once they're compressed, they can compress down to close to 40 or even 35 thousandths of an inch. But these days we have gaskets. Lots of manufacturers make gaskets that are approximately 40 thou thick, and that's the perfect amount. And so give or take a couple of thousandths of an inch in this particular realm of the combustion process is neither here nor there. So we're going to run a regular off-the-shelf Felpro type gasket, which is going to compress to approximately 45 to 50 thousandths of an inch. And because I have designed these pistons to be pretty much 0 to 3 thousandths of an inch below the deck, when these pistons expand, they will expand a couple of thousandths of an inch, and so that will mean that they're either level with the deck or maybe just above. And when the piston expands, of course, it grows up towards the combustion chamber as well. You get a little tiny bit of extra compression because the piston expands, but we're really splitting hairs here, and there's really not much in it. But I thought I'd just, before I put the cylinder heads on, I thought I'd show you those two things: the deck height, zero deck height that Ford did with the GTHO. They took 30 thousandths of an inch off, and also the removal of this machining boss that Ford had in America. And they left it on in America because the exhaust manifold wasn't an issue on this side. The clearance was an issue. The steering box was on the other side, over on the left-hand side, and so they left it. There was no need to remove it. But in Australia, it caused problems, and so Ford removed it over here. And so anyway, we'll continue with our phase 3 build. And just on a side note, I after putting the pistons and rods in and all of the clearances coming to within the Ford factory specs and the regular reconditioning specs for performance applications, I'm happy with how it all went together. And not surprising that this bottom end, it really looks quite boring and plain. There's nothing exciting about the phase 3 bottom end. It has just regular 2-bolt mains. It had the regular 351 Cleveland standard conrods with upgraded bolts. It had just the regular 4MA or 4MAB crank. And honestly, the phase 3 bottom end was particularly boring and does not look high performance at all. And so that's how Ford Australia did it. Until the next episode, I'll see you guys later.